Well, hello everyone, and welcome to today's webinar, Soil pH, Causes, Effects, and Management. I'm Chris Boomsma, Director of Education here at the American Society of Agronomy and Soil Science Society of America. It's my privilege to be the moderator for today's session. And we've got great attendance for today, and we're looking forward to kicking this off. So before we do that, there's just a few housekeeping items that I want to go over. As you may have seen in the chat feature of GoToWebinar, and now also on your screen, if you're having any issues, particularly technical issues, maybe something with GoToWebinar, maybe you got a registration or CEU question, please reach out to my colleague, Lacey Edwardson. She can resolve your issue much quicker than I can. You can see her email address and phone number on the screen at this time. And again, it is also embedded in the chat feature. Note that this webinar is worth 1 CEU, 1 continuing education credit, in nutrient management or professional meetings, depending on your certification type. Also, we will have a question and answer period, as always with our webinars, and that will be at the end of today's webinar. We'll save about 10 minutes for that. So please submit your questions to me at any time using the questions feature built into GoToWebinar. You can submit them, again, at any time. I will take those, I will order them, go through them, try to consolidate them, and then pose them to our presenters. Don't hold off to the end, submit them whenever you get a chance. All right, please note that this session is being recorded. Both the recording and the slides will be available to participants about 1 week after completion. We'll let you know when that's available. And please watch for future webinars that will be offered by ASA and SSSA in the coming months. All right, first, also, before we get started, I want to acknowledge our sponsor. We're very thankful to Economics, Nutrien, Premium Fertilizer Technologies for their sponsorship today. What is awesome is that them offering this webinar to us with a sponsorship allows us to give it to you free of charge. And they come to it doing a good job of offering a webinar that's science-based, unbiased, and inclusive, and that's the goal. So please note some of the disclaimers that I've put at the bottom of this particular slide. Sponsorship of this webinar does not imply endorsement of the sponsor's views, products, technologies, or procedures. And do again realize that we're bringing this to you as an unbiased science-based webinar and that our speaker and sponsor have committed to that mission. So with that, I do want to introduce our speaker. Today's speaker is Alan Blaylock, who is a senior agronomist at Nutrien, where he applies science-based nutrient management principles and products to solve practical problems. His experiences include farming in Eastern Oregon, teaching soil science in Iowa, serving as a soil specialist in the University Extension System, and now leading ag nutrient management programs across North America. He was recognized in 2018 by the SSSA with the Soil Science Industry and Professional Leadership Award, and in 2010 by ASA with the Agronomic Industry Award. He has a bachelor and master's degrees in agronomy from BYU, Brigham Young University, and a PhD degree in soil fertility from ISU, Iowa State University. So Alan, we welcome you today. We are very thankful that you are here. Thank you for bringing us this great science-based message on soil pH. And with that, I'm now going to make you presenter. When you're ready, sir, you can come off mute and you may go ahead and show your slides. We look forward to your presentation, Alan.
Thanks, Chris. It's good to be here again. And we hope that we have some important content for people. Soil pH is obviously a very important topic in relation to nutrient management and soil science in general. It's related to many things that go on in the soil, so we will discuss some of those things, hopefully for those who may be more familiar with soil pH. Hopefully it will be a review. For others, there may be some new material here, and so we hope it will be beneficial for everyone. So let's get after it. So, did you ever wonder why azaleas produce different colored flowers from the same plant? Well, this is related to soil pH. Azaleas growing in acid soils produce blue flowers. If they're growing in neutral or higher pH soils, they produce red flowers and everything in between. So this is just an example of how soil pH can affect plant growth. We're going to talk about some others today, and that's just a way of maybe piquing your interest a little bit, but one of the more dramatic influences, more visible influences of soil pH. So today we're going to talk about what pH is. We're going to talk about some of the chemistry and the controls of pH in the soil. What are the mechanisms that regulate or control pH that affect the soil pH? We'll talk about its effects in agriculture. How does pH affect crop growth? And then how do we manage soil pH and some of the remediation techniques if the pH is too low, particularly, but also too high. We'll get into that at the end. For many people, that's not usually a problem, but I live in the West. I've spent much of my career in the West, and high pH is more often a problem than low pH. So we'll talk about that a little bit at the end. All right, so what is soil pH? Well, it's all about hydrogen ions. There are a variety of definitions you can find in any textbook. It's, you know, the technical definition, it's a negative logarithm of hydrogen ion activity. Now remember, a logarithm is expressing units in powers of 10. So 1 unit change in pH is 10 times more or less acidic. So that logarithmic expression is very important. Another way of describing it is soil pH refers to the relative concentration of hydrogen ions and hydroxyl ions. So hydrogen and hydroxide, those are key elements of this whole pH equation. And to put it very simply, one definition I've seen, it's a numerical expression of acidity or alkalinity. So for a layperson who maybe doesn't understand what negative logarithm of hydrogen ion activity is, we simply think about it as an expression of acidity or alkalinity. And we have a scale of pH. So when hydrogen ions and hydroxide ions are exactly equal, we have what we call a neutral pH, and that is at 7. At the bottom end of the scale, 0 is where it's all hydrogen ions and no hydroxide. That's a very strong acid, highly concentrated. And at the upper end of the scale, a very strong base. The highest we can get is to 14. And there are a lot of common substances we deal with in everyday life that are all over the pH scale. So when you have that cup of coffee in the morning, you're drinking a pretty acidic material, or lemon juice with citric acid and ascorbic acid in it, your stomach acids that help digest food. Pure water is neutral, so hydrogen and hydroxide exactly equal. And a host of other things in our natural environment are all over the pH scale. When we look at soils, you can see the different soils illustrated here on the left in relation to the scale. We have, in some cases, very acidic soils. These are actually quite rare. And then the forest soils that developed in the eastern half of the US, those forest conditions tend to promote the development of more acidic soils. Now, that's also related to rainfall and soil weathering. In the grasslands, we tend to be more closer to neutral, slightly acidic. And out west, where we have salts and carbonates that have accumulated over many years over geologic time, we tend to have more alkaline pHs. pHs above 7 are very common in the West. So here's a map of the US state average pHs. So this map is generated from the soil test inventory that's conducted every 5 years, that formerly from the International Plant Nutrition Institute, now conducted by TFI. And basically, they solicit samples from soil testing labs all over North America. This data represents roughly 7.5, 7.8 million samples, I think was the exact number, submitted by all the soil testing labs. Those data are analyzed, they're standardized, and then state averages are calculated from that. You see a few states in the West where there's insufficient data to show an average, but we can see where the soil pHs are. Now, the colors of the states represent the change from the previous inventory. The most recent inventory is 2020, the previous inventory was 2015. And so you see those yellow, orange, even red colors, those are soil pHs that have declined since the last inventory. The light green are soil pHs that have stayed near the same with little change, maybe a little bit of increase. And in dark green, there's a few areas of those where soil pH has increased a bit more. Generally speaking, when we look across the continent, we generally see decreasing pH as we go from west to east. Now, with the exceptions along the Pacific coast, where there's high rainfall areas and highly weathered soils, But generally speaking, from west to east, as we increase rainfall, we increase the age of soils, the weathering intensity of the soils, we see decreasing pH. And so you see along the East Coast and through the Midwest, we have a lot of soils that are slightly acid. Many of these soils are optimum or near optimum, and we grow a lot of good crops across this region. But we also know that we have to do some things typically to maintain those soil pHs, and we'll talk about that a bit later. But so just in simple terms, we could say that as soils weather, they tend to become more acidic, and this results from the weathering of minerals, releasing hydrogen, releasing aluminum into the soil solution, and aluminum tends to promote acidity. So that's just a function of soil formation. The soil forming factors, weathering of minerals, the basic parent materials, and we see that in the pHs that we have in different areas. We'll talk a little bit more about that a bit later. All right, so let's talk about some of the effects of soil pH. What does it do? How does it affect crop response? And what are some of the things we see that are important in understanding pH? So there's a long list of things. One of the questions I had to answer on my PhD final exam was to pick a soil property that you felt was most important, and then I described why. And I picked soil pH. And the reason for that is it influences almost everything else that's happening in the soil, from biology to certainly chemistry, and even some of the soil physical properties can be influenced by pH. So there's a long list here. We could add more to that list. Some of the most important ones that we deal with in agriculture are nutrient availability, and in some cases toxicity. Microbial activity is really important, and there's a lot of attention on microbial activity in soil health these days. pH is very much related to soil microbial activity and the different types, populations of microbes that we see. So again, in agriculture, one of the more important things we deal with is nutrient availability. And this chart, or various versions of it, you can find them in any textbook, on the internet. Very popular visual expression of the influence of pH on nutrient availability. Some of the key ones that are most affected tend to be phosphorus. At both high and low pH, phosphorus availability is reduced, and we get to the micronutrients, especially the metals, zinc, iron, manganese, copper, boron. Their availability reduces dramatically as pH increases. So pH is a very important property to maintain. We want to try to maintain it in an optimum range, and typically most people would say that optimum is somewhere in the range of 6 to 7 on the slightly acid side, where we have a good, I'll say, compromise among availability of all of the nutrients. Some of the other things that are important to nutrient management is soils that are too acid can limit root growth. We get aluminum toxicities that start to restrict plant root growth. That can limit uptake of nutrients, the availability of nutrients, because we don't have good, healthy roots. Another thing to think about is volatilization of surface applied urea. pH can profoundly affect that. As pHs go higher, we tend to have more potential for ammonia volatilization. And then when soils get quite acid, where calcium and magnesium are depleted, that's one of the causes of soil acidity, is loss of calcium over years of weathering. We can actually have calcium magnesium deficiencies. In the middle of the pH range, we really don't often see calcium and magnesium deficiencies in most crops, but certainly on the acidic side, they become more limiting. Here's one of the great examples of a nutritional effect that's caused by soil pH, and this is what we call iron chlorosis. Now, iron is rarely deficient in the soil. It's a very abundant element in soils, but that iron occurs in unavailable or insoluble minerals. And the higher the pH goes, the less soluble they become. And so what we end up with is a pH-induced iron chlorosis, an iron deficiency that's not really a result of iron being deficient in the soil, but pH, making that iron unavailable to plants. And so we see these chlorotic symptoms. This intraveinal chlorosis, very classic of iron deficiency, really a pH effect. And in the western half of the US, we deal with that a great deal. One of the best ways of dealing with it is breeding varieties that are tolerant of those higher pHs, that have mechanisms, what we call iron efficient mechanisms, that are better able to take up iron. And that's a discussion for another day. It's a fascinating science, the science of the iron stress response mechanism, but it's really a pH effect that we're dealing with. Sometimes we see these effects of iron chlorosis, particularly in horticulture, very common in the West, where we have these high pH soils, and we want to plant horticultural plantings that are maybe not well adapted to our Western states. Like maybe you want to plant a red oak tree. Well, a red oak tree is really adapted to a more acidic soil in an eastern environment, does very well there. We move it out west and plant it in these high pH soils, and they're often showing symptoms of iron chlorosis. My daughter has a maple trees in her yard that she has to treat with iron sprays or trunk injections regularly to keep them green. Otherwise, they're lemon yellow. So this is a pH problem. There are, each crop is adapted to a specific pH range, and I would say that in general, most crops grow very well over a very wide range of pH, while there may be some optimum range. For example, the legumes tend to do better in the slightly acid to slightly alkaline range, largely because the nitrogen fixing bacteria that infect the roots of those crops are not very tolerant of acid pHs. So legumes that dependent on that nitrogen fixation, their optimum pH range is closer to neutral. Grasses tend to be more tolerant of acidic pHs. And we see down there at the bottom, we have potato, which is well adapted to acid pHs. Although when you look at where a lot of the potatoes are grown in North America, much of that is in the Western US, where we have high pH soils. Well, one of the specific adaptations of potato is it has this disease to which it's susceptible called potato scab, and that disease organism does not tolerate acid soils. So when we grow potatoes in acid soils, we don't see the scab incidence. When we grow them in higher pH soils, the scab tends to be more prevalent. So in that case, it's a specific adaptation of a disease organism. In other cases, it may be nutritional. In some cases, as I mentioned, the legumes, it may be due to some other symbiotic relationship. So, but for the most part, we can grow many crops in a wide range of environments, but recognize there are some that are specifically adapted to acid environments, like the azaleas that I showed. If you want blue flowers, you need an acid soil environment. So, and there are varieties that are bred for aluminum tolerance. There are varieties that are bred for iron efficiency. For example, the Northwest Corn Belt, Minnesota, North Dakota, Iowa, Nebraska. Much effort and resources have been dedicated to developing iron efficient soybean varieties that are tolerant of higher pH soils and don't show the iron chlorosis as much. So lots of various adaptations there. One of our key concerns with low pH soils is the development of aluminum toxicity. And this is important because as the soil pH declines, aluminum becomes more soluble. And you can see on this chart from Australia, from some Australian scientists, why we target remediation above a pH of about 5, because it's at that point, as we go below that pH, where aluminum starts to become problematic. Most plants will tolerate that higher pH, but few species will tolerate the aluminum toxicity that develops when we get down to 4 or lower. And that's simply because aluminum becomes so soluble and it becomes toxic. And I'll show you a picture here of some roots. Some people refer to this symptom as club root, but these are aluminum toxicity showing up in the restricted root growth. Aluminum affects the growing point. And particularly when calcium is deficient, those roots are not able to develop well. And so the plant just isn't healthy. And in many cases, it would actually die if the symptoms are severe enough. Here's a couple of pictures from Montana. And one of the issues that we've been concerned with in the Western US over the past decade or so is acidification of some of our soils that historically have not been acid. On the left here, you see a close-up of an area in a field where we have a pH of 3.8. Now think about that pH range and aluminum toxicity. And here we have a pH of 3.8 adjacent to an area 5.1 and a very sharp boundary between the two. And this pH of 3.8, you can see there's very little plant growth. Those plants will not be likely to produce a harvestable crop. So really some remediation is needed there. On the right, you see a little, an aerial view of how variable this is across the field. Now recognize that the soil properties that influence pH are highly variable. Things like soil texture, mineralogy, the topography changes, so we can have a highly variable pH across the landscape. Now, as we think about that, when we get to talking about remediation, we can talk about variable rate liming, where we apply lime to those areas most affected and lower rates of lime in the areas of higher pH. So that is a practice that is extremely effective and profitable, highly profitable, where we have these variable soils, which virtually all soils are variable and show these kinds of patterns. But you can see the devastating effect of that acid pH up close on the left and in the aerial view on the right of how much productivity is lost when the soil is allowed to become too acid. Now, the story of acidity development in Western soils is, we could spend the whole hour talking about that, but one of the major drivers of that is the long-term use of ammonium-based fertilizers, or urea being one of those. This next figure shows you a relative tolerance of different microorganism types with pH. So you see in the acid soils, we see a predominance of fungi. And when we think about natural development of soils, we have soils that develop under forest. Those soils tend to be more acid, and fungi dominate the microorganisms in those forest soils. In our grassland soils, those tend to develop a higher pH. Grasses are more effective at retaining and recycling bases, our basic cations in the soil, so they're more resilient to pH changes over the process of soil development. So in those soils, we tend to see soils more near neutral, and depending on parent material, even slightly alkaline. In those soils, the bacteria and actinomycetes tend to dominate. So you can see right in the middle there at about pH 6 to 6.5, we see a good balance of all the organisms. And as we think about these organisms, we think about the native vegetation under which the soil developed and why certain organisms are dominant in certain types of soils. And we can also think about some of the processes in soils that would be going on today. A good example of that is nitrification, which is a bacterial process. So you can imagine from this figure that nitrification is faster, proceeds faster in slightly acid to alkaline soils. And that is indeed what we see in the field. It's a bit slower in the acidic soils. We can also think perhaps about mycorrhizal infections. What are they going to look like in our more alkaline soils where the fungi are a bit less tolerant of the high pH and more favored in the acid soil? So think about the balance of some of these different organisms, the decomposition of soil, of fresh organic matter, crop residues, and all of those processes, the different organisms that mediate those processes, and how pH would affect all these different processes. So profound effects on soil microbial processes. All right, so let's get into some soil chemistry, talk about the chemistry of soil pH and some of the causes and the drivers of this. There's a lot of different things that influence soil pH, and I've mentioned some of those already, like the native vegetation under which the soil developed. Parent material can be is often a very important driver. If we contrast, say, maybe two extremes, like a soil that developed from limestone parent materials versus a soil that developed from granitic parent materials, the limestone derived soils will tend to have a higher pH naturally because limestone, that calcium carbonate is buffering that pH, where the granitic soils, first of all, they're going to form a more coarse textured soil where those bases can leach out of the soil more readily over time, but also not having the supply of that calcium carbonate to buffer the pH. So many other factors influence this. We'll talk a bit more about nitrogen specifically, talk about some of the crops, and that also relates to crop tolerance. Precipitation can be a big driver, especially over long periods of time, and how it influences soil weathering. So many factors can influence soil pH. There's probably a host of others we could list here, but we particularly think about parent material, native vegetation, precipitation. And then as it relates to our current management, fertilizer use is a big driver of those changes. And we're going to talk about that a bit more in a little more detail. So to understand soil pH, we have to understand cation exchange capacity. Cation exchange is this reservoir of exchangeable ions that are held on the solid matrix. Specific solids like clay and organic materials, particularly humus, have negative charge sites. Those sites hold and readily exchange cations, and some of these cations, hydrogen and aluminum and calcium, are really very much involved in the regulation of soil pH. Aluminum and hydrogen are the source of that acidity. As aluminum dissociates from the cation exchange complex and goes into solution, it causes a proton to be released, and it hydrolyzes, splits a water molecule, frees up a proton, a hydrogen ion, to go into solution, and that lowers the soil pH. So here's an illustration of that whole process. On the right, we see the soil solution. This is what we measure when we measure soil pH. We measure what's in the solution. Now, that is in equilibrium with the ions that are attracted to the cation exchange sites. And so you see those kind of in the middle, that cluster of ions, hydrogen and aluminum, that are close to the surfaces of the solid particles and are free to exchange with the solution. And they're also in equilibrium with what's held in or on in the minerals, for example, the more long-term residual acidity, minerals that contain aluminum and hydrogen, and as they weather, release that into the solution. And so these three major pools, as we might call them, of aluminum and hydrogen are what's governing the soil pH. So we have to understand this cation exchange process. And it's important to recognize that when we measure soil pH, we only measure what's in the solution, but there's this vast reservoir of acidity that remains on the exchange complex or in the minerals or in the organic fraction. And as we deplete the solution, those pools will release more of the acidity into the soil solution. So pH is a measure of the solution, but when we talk about liming and determining liming requirement, we have to measure this reserve acidity as well in order to understand how much lime to apply. So this process of cation exchange and the equilibration of all of these ions through these different pools is critical to understanding pH. The buffering capacity of soils is a term we use. A soil that's highly buffered is resistant to that change. If we take a little bit out of solution, we don't see a lot of change because it's highly buffered. There's a large pool of ions waiting to equilibrate with the solution. All right, so we can think about that, and this is an illustration, again, that I learned in my introductory soils class, and it makes a lot of sense, a bit easier to understand perhaps. Think of it as a coffee urn, and here we show a highly buffered soil, a clay soil. It has large cation exchange capacity and a large pool of reserve ions, reserve acidity, and the site gauge on that coffee urn reflects the active acidity. And as we put a cup under that and drain the coffee out, and that site tube drops, we're drawing from that soil solution. And in a few minutes, or very quickly, maybe in some cases, that urn will refill from the large reserve of acidity. Now, on the right-hand side, we see a sandy soil. It has a much smaller reserve. So draining a little bit of coffee out of that tube has a greater impact on that reserve than if we drain a cup of coffee out of the clay soil with a large buffering capacity. So the urn itself represents the total acidity, the soil solution, the exchangeable acidity, the reserve acidity, the sum of all of that. That's the pool that we're having to manage. The site gauge represents the soil solution. That's the active acidity that we're actually measuring. And that is in equilibrium with the cation exchange capacity, with the large volume in the urn. And drawdown of that site gauge is equivalent to depleting acidity or other ions in that soil solution, and that then becomes replenished very rapidly from that reserve. So if we can think about the coffee urn example, that's analogous to what's happening with cation exchange. Okay, now I know this is a complicated graphic, but let's talk about the nitrogen cycle and soil acidification. Now in this graphic, the red lines represent, and you can see the little red H's there with a little arrow, those processes represent the donation of a hydrogen ion into the soil solution. So if we look at all of these nitrogen processes, we have lots of red lines. There are lots of components of the nitrogen cycle that donate hydrogen ions or donate acidity, produce acidity in the soil solution. There are a few places where a hydrogen ion is consumed, and you see those green hydrogen ions. There's a couple of places where a hydrogen ion is consumed in a nitrogen process. And there are some processes that are neutral, like the uptake of nitrate. That would be accompanied by a cation. So when the plant takes up nitrate, it would likely also take up a cation to accompany that. So when that nitrate is accompanied by a cation, there's no net change. The uptake of ammonium, on the other hand, the plant releases a hydrogen ion to balance that charge. So if it takes up a cation, it has to release a cation, or it has to balance it with an anion. So it may take up an anion to accompany the ammonium, or it may release a cation to balance that ammonium that's being taken up. And those cations are usually hydrogen. So the roots secrete hydrogen to balance the uptake of that ammonium ion. One of the most important processes in the nitrogen cycle that affects pH is nitrification. You look at this ammonium ion here, and there's 4 hydrogens associated with that nitrogen. When we convert that ammonium to nitrate, all 4 of those hydrogens go into the soil solution. So nitrification is an acidifying process. So what are most of our nitrogen fertilizers? Most of them are applying at least some of the nitrogen in the ammonium form. Anhydrous ammonia, urea, which is an ammonia, essentially ammonium form, ammonium nitrate, where half of the nitrogen is in the ammonium form, ammonium sulfate, where all of the nitrogen is in the ammonium form. All of those ammonium sources convert to nitrate ultimately, often fairly quickly. And over many years of using ammonium sources, we contribute a great deal of acidity to the soil. So you remember those pictures I showed you from the Montana wheat fields. The acidification of those fields is related to the use of ammonium nitrogen fertilizers. We can think about urea. The process of urea hydrolysis initially absorbs a hydrogen in that process, but then that hydrogen gets released again as the subsequent ammonium nitrifies. So this cycle, this nitrogen cycle, again, lots of red lines, lots of places where hydrogen is released into the soil environment, and that over a period of time contributes to soil acidity. Now, down at the bottom, we see this carbonate buffering, and carbonate and bicarbonate are the primary buffers throughout most of the middle of the pH range. They really control or buffer the soil pH against these changes because they absorb hydrogen ions. So calcium carbonate, as it dissolves in acidity, the bicarbonate absorbs a hydrogen ion. The calcium is released into the soil solution, and the bicarbonate dissociates into water and carbon dioxide. So that's a process by which that hydrogen ion may be removed from the soil solution. We'll talk about that process a bit more when we talk about liming. But anyway, keep in mind, nitrogen is one of the nitrogen cycle is one of the key drivers in the development of soil acidity over many years of cropping. So when we look at some of the various fertilizers and what we might call their acid equivalent or calcium carbonate equivalent, here's a list with some numbers. So for example, urea, the calcium carbonate required to neutralize the acidity produced from the use of that fertilizer is almost 2 pounds of calcium carbonate per pound of nitrogen. Ammonium sulfate, a very acidic material. Again, we have 2 ammonium ions in a molecule of ammonium sulfate. Ammonium sulfate itself is acidic in nature, same as MAP, but we also have the nitrification process from all of that nitrogen. So you can see that the use of these materials over time contributes to acidity, and if we're not maintaining our liming program, the pH continues to decline. Here's an example of that. This is a study from Saskatchewan. Over 9 years of urea fertilization, you can see the different N rates, 0 N, 40 pounds of N per acre, and 160 pounds of N per acre annually. And you can see how much difference that made in pH. If we look particularly at the surface, we have about 3/4 of a unit change in pH with 160 pounds of nitrogen per year over that 9-year period. So that's really a relatively short time period for that large a change in pH. And you see that that effect actually is not just at the surface, it's throughout the upper part of the soil profile where that nitrification is occurring. And you can see at that 3 to 6 inch depth, we're getting down into the range where aluminum toxicity would begin to be manifest. So this is an important factor to understand. All right, so let's talk about remediation now, and this is our management aspect of this whole thing. When we want to raise the pH of acid soils, we call that process liming. And it consists of a couple key components. We have to supply a calcium source to displace the exchangeable hydrogen. Now remember, we're trying to neutralize not just the acidity in the soil solution, but we're also trying to neutralize that reserve acidity as well. Because if we just neutralize the solution, it's going to equilibrate and we'll have really no real effect. So we have to supply something to displace that exchangeable hydrogen, move it into the soil solution, and then we have to add a base to neutralize that hydrogen. And in the case of limestone, that base is carbonate. So we have calcium and carbonate. Calcium carbonate is what we call limestone. We can have magnesium carbonates, which are also effective. We may have oxides or hydroxides. Any kind of source of calcium coupled with some kind of base to neutralize the acidity is what we're looking for. Now, the efficacy of that material, the overall value of that material will be based on on several components. One is, what is the chemical composition? Is it calcium carbonate, calcium oxide, calcium hydroxide? What is the basic chemistry of the material? particle size. How fast will that material react? The more finely ground the material is, the faster it will react with the soil solution and neutralize the acidity. If the material is too large, we might not see any real liming value in that material over even a number of years. And then the third factor is how pure is it? If it's pure calcium carbonate, it's going to have more liming value than, say, a limestone material that maybe has a lot of clay or inert other materials in it that don't have liming value. So we look at these three things. They're basically multiplied together to get an effective calcium carbonate equivalent. And that's how we score the value of a lime material, and it would be priced proportional to that liming value typically. So the ideal would be pure, finely ground calcium carbonate, and that would have a value of 100 if it's pure. And then everything else would be compared to that. Now, again, remember, pH only measures that active acidity. In order to determine how much lime to apply, we would use a buffer pH method. And so when you get a soil test, if you have an acid soil, it will often be accompanied by a buffer pH measure. And that buffer pH measure attempts to quantify that reserve acidity and give us an indication of how much lime would need to be added. So it's simply a buffer solution that is able to absorb that reserve acidity, extract that, and then through the use of tables, calculations, and calibration of that method, we get to the reserve acidity and the lime requirement. Now, many states or provinces publish tables that also give us an approximation of how much lime to apply. If we have a buffer pH, we look up the liming value. We know our starting pH. We have the buffer pH. We look up that value in a table, and we can from that get the amount of lime to apply. So that's how we arrive at that. But we have to have something more than just pH. Sometimes it's estimated from soil texture, although that would be a very gross approximation and less accurate method of doing that. But given soil texture and some understanding of cation exchange capacity, we can make a gross estimate. So you'll see tables like that. And if you need to apply lime, you consult the local recommendations, the local tables, and recommendations for that. All right, so how does lime neutralize soil acidity? Well, we've alluded to this already in talking about some of the reactions that occur. When we have a soil with exchangeable acidity, we add calcium carbonate. That calcium carbonate will dissolve in an acid environment. It's slowly soluble, and that dissolution releases calcium. Calcium has a stronger affinity for the cation exchange sites, so it will be attracted to the exchange sites, kick off the hydrogen into the soil solution, where that hydrogen would then combine with carbonate, would be neutralized by the carbonate. It would form bicarbonate or carbonic acid, which would dissociate into water and carbon dioxide. That's basically the liming process. Now, this same process works in reverse if we want to lower the pH of a high pH soil, but we use different materials to affect a different result. But this is how liming works. Again, we have to have a source of calcium to displace the hydrogen on the exchange complex, and then something to neutralize that hydrogen. Here's a list of some assorted liming materials. They're calcium carbonate equivalent, and again, this is based on the chemistry and the molecular weight of these different compounds. Calcitic limestone would be the most commonly used material. If we need magnesium, say, for example, we have a magnesium deficient soil, we might want to use a dolomitic limestone, which also contains magnesium carbonate in with that calcium carbonate. Marl is simply another form of calcium carbonate, typically occurs on coastal areas where calcium carbonate is precipitated. Other sources, hydrated lime, slag, which is a calcium silicate material, burned lime, other lime byproducts. For example, in the West, where we have sugar beet processing, lime is used to purify the sugar to get it to crystallize, and the spent lime from that process is sometimes available as a liming material at relatively low cost. Now, I have gypsum in this list. Gypsum is a calcium salt, a calcium material, but so we supply the calcium, but what's missing in that gypsum? Well, what we're missing is a base to neutralize the acidity that's displaced from the exchange site. So while we can supply calcium, it's a neutral salt and doesn't neutralize the acidity. So it might be a good soil amendment for certain soil properties, particularly sodic soils, which that discussion is an entire presentation in itself. We'll reference that here a bit shortly, but that calcium sulfate is not a good liming material because it doesn't have the neutralizing value that we need. All right, so how do we determine that liming material effectiveness? So here's how we would go through that calculation. We take the molecular weight of the material, we relate that to calcium carbonate, arrive at the equivalent percentage. We multiply that by the purity. So if it's less than 100%, which most liming materials would be something less than 100%, we might be mining those materials and have other foreign material in it or non-neutralizing salts. And then we multiply that by the fineness factor, and that's really determined from the mesh size of the material, and then we get to that effective calcium carbonate equivalent by which the lime is valued. So if we look at the fineness effect by itself and simply look at materials of different mesh size, you can see that particles greater than 8 mesh material, you get very little liming value out of those even over a period of several years. But if we have a less than 60 mesh, so really finely ground material, that virtually entirely racks in a single year. So finely ground materials provide much faster neutralization, give you greater liming value. So why put lime on if it's going to take 10 years to react? So you're spreading rocks then, basically. We don't need to add gravel to a lot of our soils. So fineness is an important factor when we're applying soil amendments. To determine liming frequency, we just want to be monitoring our soil pH. And as we see that start to drop lower than our target pH, well, then we make that change. But there are a variety of things that can influence the rate of acidification and therefore the liming frequency. Now, we may contrast, say, a sandy soil that doesn't have a lot of buffering capacity, doesn't have a lot of cation exchange. We're not going to be able to apply a large amount of lime at one time and get the value from it, but we would likely have to apply that more frequently simply because the buffering capacity is less. In contrast, a clay soil with a high cation exchange capacity, high buffering requirement, we may be wanting to apply a high rate, but maybe we don't have to apply it as often because as we load the cation exchange up with calcium, it will be more resistant to pH change. And some of the things that are going to influence that in terms of soil properties and our management, we talked about nitrogen. Different crops remove different amounts of calcium, magnesium. For example, alfalfa takes up a lot of calcium, so it's going to deplete that calcium buffer more quickly. And irrigation, particularly if we have any leaching occurring that carries some of those bases with it, that can relate to more rapid acidification. All right, so we've talked about nitrogen a bit, and just to add a little bit to that, if nitrogen is going to be a key driver of our development of acidity, anything we can do to improve nitrogen use efficiency, so avoiding excess rates, using best management practices, using other substances to reduce nitrate loss, such as slow release or nitrification inhibitors or urease inhibitors, planting deep-rooted crops to make sure we scavenge available nitrate that may be deeper in the profile. Anything we can do to make that system more efficient, we can slow the acidification from nitrogen materials. And we can also look at other nitrogen sources, such as calcium nitrate, which would not have an acidifying effect. Now, unfortunately, those materials like calcium nitrate, calcium ammonium nitrate tend to be a bit more expensive. But where they're available, where it may suit the cropping system, may be appropriate, would be a way to slow the acidification from nitrogen fertilization. All right, so let's wrap this up. Let's talk briefly about what if pH is too high and I want to reduce the pH. Well, there are kind of two basic problems with high pH soils. The first of those is really nutrient availability. We talked about phosphorus and micronutrient availability. As pH goes up, they become less available. Now, we have to take a look at that and say, how serious is that problem? For example, iron chlorosis. Is it just small areas of the field? How serious is the economic impact of that nutrient availability? And is there another way I could manage nutrients without modifying the soil pH? Because acidifying high pH soils is a very expensive process. The amendments are more expensive. It's typically very difficult. We're typically trying to neutralize free lime in the soil that's supporting that pH. So what are there other solutions? Might I be able to manage my nutrients in a different way, perhaps through placement or using more acid materials? Maybe I can band my phosphorus with another acid forming material like ammonium sulfate and get a better result without actually modifying the pH of the soil. Can I apply micronutrients in a different way that makes them more available, such as foliar applications or again banding or chelated forms that may be more available in acid or in alkaline soils. So we can look at that as a nutrient problem. The other problem that we have with high pH soils is when we have sodic soils, and that's where sodium then takes over and dominates the exchange complex. This creates some serious physical limitations in the soil that really have to be remediated. And these are some of the most difficult problems to solve in soils. They're caused by poor drainage, poor quality irrigation water primarily, and those problems may not be easily rectified. But if we have those problems, we really need to try to do something about it. So when we look at remediation, again, we're looking at two distinct problems, one related to nutrient availability, but for sodium affected soils, we probably also need to look at amending soil physical properties. We may need to alter the drainage of the soil in some way. We may need to alter irrigation water supplies, and we have to add some amendment that supplies calcium to displace that sodium. So we have to displace the sodium from the exchange sites and then leach that sodium out of the soil. And that's really the only long-term correction for that problem. The most common material probably used for that is elemental sulfur. Sulfuric acid is also very effective. Essentially, elemental sulfur in the soil as it oxidizes converts to sulfuric acid, essentially. Lime sulfur, another acidifying material. These are the most common amendments that would be used. For long-term maintenance, adjusting nutrient practices for better availability. We may want to use ammonium fertilizers in these situations, grow acid-producing plants, neutralizing carbonates and bicarbonates in irrigation water. Some people with high bicarbonate in the water actually add acid to the irrigation water to neutralize that so it doesn't get to the soil. So the remediation of these issues can be quite complex. And if it's just a nutrient issue, we may be better off just managing our nutrients and making adjustments. Here's a table showing approximations of the amount of elemental sulfur that would be needed given an initial pH and getting to a pH of 6.5. You can see we're looking in some cases at more than a ton of elemental sulfur per acre to make that pH adjustment. So it takes a lot. We're not talking about nutrient rates. We're not talking about 20 or 30 pounds per acre as we would apply sulfur as a nutrient. We're talking about a soil amendment for which large amounts would be required. So you can see this would be very expensive. Now that works. These are the amounts listed for a carbonate-free soil. But what if I have a soil that has 5 or 10% free lime? We would have to neutralize all of that lime before we're going to affect a change in pH because that's our buffer capacity. So it can become even more expensive if we have free lime in the soil. So just, again, if it's just a nutrient problem, we can manage nutrients perhaps in a more economical way. Kind of running out of time, so I'll skip this last one and let's just wrap it up and say liming is a relatively inexpensive process and almost always delivers a return on that investment. If we have acid soils that need to be limed, those are going to affect crop growth, and the return on that investment will often be significant. Using sulfur or some other acid forming amendment to decrease soil pH of a high pH soil, unless we have these sodic soils that really need to be fixed, there often is not an ROI for those. Now, I would put a caveat on that. In horticultural situations where we maybe are dealing with a small area or a very high value crop, I can do things in my garden, for example, that I wouldn't want to do in a large acreage. So we need to consider the environment. There may be times when adjusting that pH downward might be beneficial. All right, so we've defined what pH is. We've talked about the factors that affect pH, how important it is for plant growth, and we've talked about managing and amending soils to maintain pH for long-term soil health and optimum crop production. So with that, I will give you some contact information here. Check out our website, nutrient-economics.com. That's our nutrient agronomy website. Lots of different educational materials there. There's my email address if anyone has questions beyond this webinar and would like to discuss them with me. That's a good way to reach me. So with that, Chris, I will turn it back to you for any questions.
Well, thanks, Alan. Yeah, we do have plenty of questions that have come in today. Certainly, folks, we will not be able to address all of them, not even close. But do make note of the economic website put up on the screen at this time, and also Alan's email, because I think you're going to have to reach out for follow-up at some point here. Alan, I'm just going to pose some basic questions that might be of broad interest here, given our restricted time. Let me start with this first one, and that is, what is the effect, Alan, of drought on soil pH in the near term and in the long term, given all the drought we've seen across the United States and elsewhere on the globe as of late? Any comments and thoughts on that?
Yeah, so I would say, generally speaking, my thought would be that drought probably does not significantly affect the pH other than temporarily. So if you don't have a lot of soil moisture, the concentration of elements in that soil solution could increase, right? Simply because there's less water. So you might see a temporary change in the measure of pH, but the chemistry hasn't really changed. Now, if we contrast that to a year where we have lots of water, for example, and we have maybe continual leaching of that acidity over time, what that drought might do is kind of suspend some of these acidifying processes for a period of time. But I would expect those effects to be temporary. Now, the exception to that would be where we have evaporation exceeding precipitation. We can have water moving up through the profile and bringing salts basically to the surface, and some of those would be bases that might alter that pH measurement. So we can certainly bring those salts up to the surface. That's common if we have high water tables that are below the surface, dry soil at the surface, then those reactions can occur. But I think those effects of drought would be largely temporary. So I wouldn't want to overreact if I see a pH that, whoa, this is a lot different from last year. I wouldn't want to overreact to that.
Awesome. All right, thank you, Alan. Just one more question, then is probably all we have time for today, folks. It's a basic question about fertilizers. Alan, why would we continue to use ammonium-type fertilizers on soils that are known to be turning acidic? And maybe a follow-on question, should people pivot away from those type of fertilizers to something else if they're having a soil acidity problem over time?
That's a great question, and I don't know if there's a really good answer for that. I would say, why do we continue to use these ammonium fertilizers? Well, things like anhydrous ammonia and urea are our most economical nitrogen forms. That's really, and they're good fertilizers. High concentration, high purity, easy to handle, easy to use. So we continue to use them for agronomic reasons. They perform well and they're low cost. As I mentioned, if we switch to some of these other materials, they're less widely available, and two, they're higher cost. So the person has to weigh the effect of the cost benefit of the long-term progression of acidification versus the cost of liming. If switching to another nitrogen fertilizer is going to slow that process down and that's more cost effective than liming, well, then I might want to do that. If lime is readily available, then liming is still going to be needed anyway. And so I would want to stay with that plan, and liming may be a more cost-effective solution than switching to a more effective neutral nitrogen fertilizer. So that's a really complicated question, and I don't know if there's a good, clear answer. In areas where lime is not readily available or is high cost, well, then I may want to look at those other alternatives, other ways of managing that problem if I don't have good access to liming materials.
Great. Thank you, Alan, for that answer. And thank you for this entire presentation today. Lots of great questions. Again, folks, follow up with Alan directly, please, or check out nutrien-economics.com for maybe some of these answers that you're looking for. Otherwise, thank you again, Alan, for everything today. Thank you to our sponsor, Nutrien Economics. Again, that sponsorship brings this science-based education to you free of charge. Please check out the chat feature one final time if you have questions regarding your CEUs and also the webinar recording. Again, you will have access to that recording in the slides. With that, please join us for future webinars. We thank you for joining us today. Have a wonderful day and a wonderful week, everyone. Bye-bye.
Thanks, Chris.